Right now, this little machine is running a 70 billion parameter AI model. And so is this one and this one, all three together. But here's the part that doesn't add up. Not one of them is big enough to hold this model. Not even close. By the way, this is Intel's newest silicon, a brand new chip, a brand new GPU, a dedicated AI chip sitting on top of that, the NPU, and I got 3 of them to try something crazy. So how is it running a model that none of them can actually fit? Okay, so the dream here is simple. Mini PCs are getting pretty ridiculous. And if you're a developer, this is pretty convenient stuff here. Not only will it run your IDEs and code smoothly now, these used to be kind of a joke just a couple years ago. Now they're serious. These things can also run AI locally. Your own models, your own data. No API bill showing up at the end of the month. I have it next to my Mac Mini to show you the relative size of this new one. It's shorter, it's narrower, it's a little bit longer than a Mac Mini, but it is pretty small. The question is, can you take a few of these and bolt them together into one machine that runs stuff that you couldn't run on just one? The part that people forget about a clean local setup is what happens when you need storage somewhere else. For anyone dealing with servers, datasets, checkpoints, or large project files, storage gets complicated fast. You want redundancy and remote access, but you don't want to give up privacy just to get it. Most services make uploading easy, but they're not really built around the idea that your data should stay private. That is where Internext comes in. It's a privacy-first cloud storage platform built around keeping your data under control. Your files are protected end-to-end, zero-knowledge encryption, so only you can access them. Not even Internext can access them. It also uses post-quantum cryptography to help you protect against current and future threats. And it fits real workflows too, with web access, desktop, and mobile apps, plus CLI, WebDAV, rclone, and NAS support. Yeah, I can sync my NAS right to it. I like this more as a companion to a local setup, not a replacement for it. On top of storage, you also get privacy tools, file versioning for supported file types, and the lifetime ultimate plan gives you 5 terabytes for a one-time payment. No subscription. So the pitch here is simple. Private cloud storage that actually fits the way technical people already work. This is not just vague security language. Internext is open source and independently audited by Securitum. It's also GDPR compliant and ISO 27001 certified. Use my link in the description or go to internext.com/alexiskin and use code alexiskin to get 87% off the lifetime 5 terabyte plan. So in case you're not familiar, Asus just released these. These are the NUC 16 Pro. This particular design actually varies quite a bit. You get Wi-Fi 7 and Bluetooth 6 in these, and they carry the Pro name because they have redundancy for pretty much everything. 2 Thunderbolts, 2 HDMIs, 4 USB-As, dual Ethernet ports, upgradable RAM, but they can come with Intel Core Ultra 5, 325 for $559, Core Ultra 7, 356, and these are Core Ultra X7, 358H, so this is like the high-end ones. Here's my favorite part though. If you want to get inside, it's just a little pull tab like that. More mini PCs should be doing this kind of thing. Look how easy it is to get in and get out. Done. I was inside of that just now. They can actually get up to the Intel Core Ultra X9, which I don't have, but I'd imagine those would be pretty crazy. They also have the new Arc B390 GPUs inside, and a separate NPU that's the dedicated AI engine. Now, my version also comes with 64 gigs of memory. This one on Newegg has 32, and it's already at $1,700, so you can imagine how much these cost. Check the current pricing, because that's always changing. Now, even though there's definitely no question that these would make incredible little dev machines, I'm gonna be doing something you probably shouldn't be doing with them, making an AI cluster out of them. And that dual Thunderbolt that I was talking about, keep an eye on that because it comes back later in a big way. So if you've been watching this channel at all recently, you know that I have a few machines here that I've been clustering, including these Dell GB10s, which are basically the same thing as the DGX Spark, and the Mac Studios, and all those machines can be clustered using RDMA, which basically means, you can go back and watch the videos, but basically that means that the more machines you add, the faster it gets, generally speaking. This is basically for things like large language models, LLMs. When you're generating text, generating images, if you decrease the network latency between the machines, you're gonna get faster generation. And when you're doing text generation or image generation and whatnot, there's always 2 stages. One is prompt processing. If you're working with code, for example, and you've got your IDE talking to an LLM for code generation or debugging or whatnot, you're going to be sending all that code as context to the LLM. That's where prompt processing comes in handy. So prompt processing has to be fast. I won't get into the details of that setup in this video because I have a bunch of other videos showing that. Now I just want to test how fast these things do that. And the first thing I wanted to know, on a brand new chip, can that new Arc GPU actually speed up an LLM? So I ran the same model on the CPU and then on the GPU. Turning the GPU on essentially doubles the speed that it reads your prompt. Just over 1,000 tokens per second up to 2,200 tokens per second. Boom. Nice. The second part of LLM's inference is token generation. After it's done as prompt processing, it switches over to the generating part. And that right here, my friends, is about 46 tokens per second on the CPU and about 46 tokens per second on the GPU. It didn't move. And this is the thing I want you to remember because it comes back to haunt us the rest of this video. This is the memory wall. Token generation relies on memory bandwidth. Prompt processing relies on that brand new hot GPU chip that's really fast. Both sides are very important. And on these particular chips, the Panther Lake chips, the GPU shares the same memory as the CPU, and generating text is limited by that memory speed. So the GPU's extra muscle does nothing for it. For the generation tokens per second, memory bandwidth is the boss. So the GPU helps, but it's not magic, and there's still that third engine that I hadn't touched, the NPU. If the GPU is capped by memory, maybe a dedicated AI chip is the real story, right? So let's get into the game. First problem, the tool that we can use on these machines, the most popular tool for doing inference is llama.cpp. It can't even talk to the NPU. So I switch over to Intel's own OpenVINO. This is Intel's own software. And small model on the NPU actually works. Cool. By the way, if you're not familiar with OpenVINO, it's supposed to be able to use the GPU, the CPU, and the NPU, and basically automatically decide for you which is best. And OpenVINO has their own toolkit and models on Hugging Face. And these are specifically OpenVINO models with an OV extension, so you can know what they are. Because Hugging Face model naming conventions are so convention-y. Right. And then I try a bigger model and it fails. Intel's own pre-built models will not run on Intel's own NPU. So I had to go and rebuild the model myself just to get it to load. That's the bleeding edge for you. But we know these days what happens with these chips. They come out, they're great, but if you want to do any kind of bleeding edge AI stuff, the software has to catch up. However, once I got it running, here's all three engines across a few models. Small-ish models. GPU is fastest everywhere. But the NPU beats the CPU. It's just not a speed demon, and it's a bit slow to spin up. Now hold on, I just used two completely different pieces of software, llama.cpp for the GPU and OpenVINO for the NPU. But I did mention that OpenVINO also works on the GPU. So on the exact same GPU, which one is actually faster, OpenVINO or llama.cpp? Well, I ran that too. Same model, same chip, and I did not expect this. The free open source tool beat Intel's own software by about 2.5 times. 34 tokens per second with Vulkan. Vulkan is just the API that llama.cpp was using in this case, versus Intel's 14 tokens per second. On Intel's own GPU, come on. So file that away, because when we get to the cluster, we're gonna be sticking with llama.cpp here. It's faster, and it's really the only way to get clustering going anyway on this particular setup. But there's one more thing that I wanted to settle before leaving one single box. Speed was never NPU's whole pitch anyway. Efficiency is. Everyone says their NPU is the most efficient one, and everybody's got an NPU now. Okay, let's actually measure it. Real watts while it's generating. And the answer is both things are true. The NPU actually draws the least amount of power, 17 watts, versus 24 for the GPU, versus almost 30 for the CPU. And the power draw, the NPU has the lowest draw, it's the coolest and the quietest. That part is real. However, the GPU is actually more efficient per token. That's that red line right there. Because it's twice as fast. It finishes the work sooner and uses less total energy per token. And usually you're going to be doing these kinds of bursty operations on a machine like this, unless you're running agents 24/7. So the NPU sips the least power, but the GPU gets the most AI done per joule. The CPU it loses on both. But that's kind of always been the case. However, the CPU is making a comeback, and I'll talk more about that in future videos. So the whole lesson from one box, memory bandwidth runs the show. So I squeezed everything I could out of one machine. The only way to go bigger is more machines. I brought in the other two NUCs, wired them all together, and split one model across all three. More machines, more speed, right? No. I was kind of hopeful, but now I'm a little disappointed. But we've seen this story before with my framework video cluster situation before I got RDMA working on that, and my Minisforum cluster video. It got slower. The same model on one machine was about 35 tokens a second, and across all three, 17. It got essentially cut in half. This is Qwen 3.635 billion, by the way, which easily fits into one machine. Once you see why this happens though, it all makes sense, even if it stings. This kind of clustering splits the model into chunks, and every single token has to hop from one machine to another machine to the third machine over the network. Over these Ethernet wires, going to the switch and then back. You're not adding power, you're adding traffic. So we have the same memory wall as before, but now we've just added the network tax on top of it. So if clustering doesn't make a model faster, what's it actually for? With a caveat that I've mentioned before, clustering can make inference faster if you're using the right technology, which is RDMA, which I'm showing in other videos, and I'll link those down below. But the answer is the whole reason I did it. It's not for speed, it's for size. Let's find the model that no single one of these machines could ever run on its own. Ah yes, the good old Llama 3.370B. This is a dense model, it's large, it's been around for a little while, but all the models have been either mixture of experts models, which means they have a certain number of parameters, like 200 something, but they only have a small number of active parameters. So they've been bigger in parameter count than the 70B, or much lower in parameter count than the 70B, but they're not really dense. They're a mixture of experts. This one is dense, and the one I ran is 75 gigabytes. A single machine has 64 gigs of memory. It physically cannot load this, period. But three of them together, that's 192 gigabytes in the pool. So I split the model across all three, and it works. It actually works, folks. Three little machines, not one of them big enough on its own to run the 70 billion parameter model. It's slow, okay? 1.4 tokens a second. But that's not the point. The point is, it ran. And the fun part is that I asked it what is remarkable about three small computers running one big AI model. And it described its own situation right back to me. Okay, so it works, but it's slow, and every one of those tokens is hopping between the machines over plain 2.5 gig Ethernet. The fix seems obvious, right? Make the network way faster. Each one of these machines has two Thunderbolt ports on it. Remember that second port I told you about? 20 gigabit, like 8 times the bandwidth. So I wire all three together in a triangle. Every machine straight to every other one. This has to fix it. And it did basically nothing. Loading the model got a little faster on the small one, but the big 70 billion parameter barely budged. And generating tokens on the 70 billion parameter, it was identical. 1.43 before, 1.43 after. The smaller model actually got worse, and it kept crashing. Now here's why. It's the same wall from that very beginning. The bottleneck was never the cable or the bandwidth speed, it's memory speed, and thousands of tiny little messages flying back and forth every second. A wider highway doesn't fix the traffic jam that isn't on the highway. Well played, physics. Splitting one model across machines is a dead end for speed. But there is a completely different way to use these three as a cluster. And I've shown kind of a demo of this in a previous video. We don't split the model at all. We put a full copy on every machine and just send each request to a different one. This, of course, will only work for models that will fit inside the RAM of one machine. By 70 billion parameters. Aha! This one scales. One machine handled about 196 tokens a second under load. Three machines, almost 500 tokens a second. 2.5 times faster, finally. So here's the rule, and it's the whole thing in one line. You cluster one way for size, you split the model, and a completely different way for speed and for throughput. Copy the model and spread the work. Don't mix them up. So step back and look what actually happened here. Same lesson at two different scales. There's 3 AI engines in one box, or 3 boxes in one cluster. Now I think that this could be solved at a software level to some degree. I'm not 100% sure about that, but Apple did it, just magically updated the software and suddenly RDMA works. Donato Capitella in his videos, by the way, his channel is somewhere down below also, he got it working with his Strix Halo boxes. I did the same thing following his example. So maybe there is a way to unlock that in software here. Is the newest Intel stuff ready with the software stack? The hardware is real and it's impressive, but the bleeding edge means rough edges. Intel's own software wasn't ready for Intel's own chip. I'm rooting for them. They've made some really nice leaps recently, especially with their discrete professional GPUs, and I've made a video about the B60, B70. You can check all those out. So if I were you, for a model that fits on one machine, the cluster is kind of pointless. One box wins every time. A cluster like this would be better served as a Proxmox serving virtual machines, for example. This whole setup only earns its keep and its price tag when the model is too big for any single machine. Or you've got an office of people and you want to serve them. I'm curious, if you were to run a cluster like this with mini PCs that are APUs, for example, like this one, would you run it for AI or would you run it for Proxmox or virtual machines? What would you do? Let me know in the comments down below. Very curious to read that, and I read all your comments. Do check out that cluster setup right over here and the framework cluster setup over here. Thanks for watching, and I'll see you next time.